Hello, students. This is Dr. DA, and welcome back. This is an activity called Experiment 9A in your lab manual. It is the titration of an unknown solid acid. Now, because we have moved towards remote instruction, you will not be physically able to do this actual experiment. So we're going to do what we call a virtual or dry lab. Before we begin this introductory video, I did post a link to a website where you can watch a YouTube video where you can review all of the techniques of titration. Be aware that that's a professional video for an analytical lab setting, so they do a few things kind of beyond the scope of what we do, but it should give you just a refresher of what titration is all about, because that is the technique that you will use in this lab, okay? So let's go over here to our makeshift whiteboard here, and let's look at what I have written here. Uh, since we began our study, one of the important things that we said chemists have to do is to find the molar mass of compounds. Why? Well, typically what we're looking for is we're trying to find out what is the chemical formula of our compound. But what our experimental analysis gives us is the percent composition of the substance. In order to find the chemical formula from the percent composition, we need the molar mass. All right. Now, previously we discussed two methods by which we can do this. For gases, if we know what volume a certain amount of gas occupies at a certain pressure and temperature, we can use the ideal gas equation to find out the number of moles. And since we know the grams and we know the moles, we can find the molar mass. We can also use Graham's law. In Graham's law, we compare the rates of effusion of two gases, one known, let's say 1, and one unknown, 2. And Graham's law says that if we want to find out the molar mass of our unknown, the rates of effusion are inversely proportional to the square root of the ratios of their molar masses. So we can use Graham's law to find our unknown. In this experiment, we are going to be working with an unknown acid. And I asked the question here, let me block this a little bit. How do I know that it's an acid, right? Now, you already kind of peaked, but anyway, the idea would be you put it in water and you do a litmus paper test, right? And we know from our previous experience that an acid will turn blue litmus paper to a pink color, all right? So let's go and look at the typical process that happens when an acid reacts with a base. Here is a typical acid. Let me explain briefly what these things mean here, all right? Remember that when an acid reacts with a base, and here I am representing the acid as HMX, all right? The subscript here represents the number of hydrogens that this acid has that are ionizable or that can be transferred, right? Remember that in the Bronsted-Lowry definition of what an acid is, we said that an acid is a proton donor. Right? In this case, what we're saying is that this particular acid is capable of donating M units of hydrogen or hydrogen ions, right? And in this reaction with KOH, as you can see, those hydrogens are transferred to the hydroxide ion here to form water. And the potassium and whatever the ion here, X is, they form a salt. So one of the questions we can ask is, well, what is happening to the acid here? What happens to the acid? Well, we could say that our acid, HMX, essentially separates or dissociates into M ions of hydrogen and let's say some kind of uh, negatively charged or anion that has a charge that would have been equivalent to as many positives as this was. So let's call it M minus. So if this had been H2X, then this would be Z. I mean, sorry, X. I'm sorry, I have Z there for some reason. X would have a charge of -2 in that case, for example, right? But there's another question we can ask instead of what happens to the acid. What we can ask is what did the acid do? Well, in this case, what we see is that based on the stoichiometry of this reaction, there were a transfer of M units of hydrogen into M units of KOH. To keep the stoichiometry, of course, we are producing, M units of water. And of course, to balance the charge out, that means that we needed that many potassium ions to balance the charge on the anion here, all right? So that M comes from the balancing the equation and following stoichiometric ratios. But when we say, what did the acid do? We would say that the acid neutralized M units of KOH. In this case, what we're kind of like focusing on is the chemical activity, the chemical power of this acid. And we would say that an acid such as, let's say, HMX has M equivalents. An equivalent represents the number of units of base that one unit of the acid can neutralize. So for example, HCl, we would say that since it has the capability of transferring one hydrogen, then that means that it can neutralize one unit of base for every mole. So we have one equivalent per mole. On the other hand, sulfuric acid that we have encountered before has two hydrogens that it can transfer, and therefore it can neutralize 2 units of base, or we would say that there are 2 equivalents per mole of sulfuric acid. In other words, when we look at the substance this way, we are not measuring how many units we have, but what kind of chemical power is contained in a sample of that substance. So let's say that I now have an acid of unknown composition. I don't know what this acid is. But what I can do is I can measure a sample of known mass, right? I can do a sample of known mass. And what I can do now is I can react it with standardized KOH. Well, that's what you're going to do. You're going to be given an unknown acid, and you'll be using the KOH you made in the previous experiment that you standardized to find out how much of it reacts with your sample of acid. So by finding out from the standardized KOH, because you know its molarity exactly, you can find out how many units of KOH reacted. And therefore, you can find the number of equivalents. In other words, the amount of power to neutralize units of KOH that was present in that sample. And so we can determine something called the equivalent mass. sometimes called the equivalent weight also, because here in America, we sometimes use those interchangeably, as the number of grams, because we know what that is from our sample measurement, divided by the number of equivalents. So whereas in other contexts, we're interested in, well, if I have a sample of this compound, how many moles do I have? Well, in this case, I don't know the formula. I don't know who the compound is, but I can measure what is the chemical activity of that sample, and I can represent it in the form of the grams per equivalent. That tells me in a sample of X grams, how many equivalents of, neutralizing power do I have? Or alternatively, how many grams of that acid does it take to neutralize 1 unit of base? Okay, it's a way of measuring the chemical power, the chemical activity of something. Now, here is your lab that you're going to be carrying out today. And let me zoom in a little bit here in on it. As always, they give us these, lab manual gives us these experiments in a paragraph form, and it's kind of hard to read. So just as usual, if you had been doing this experiment, on site, you would have had to write a pre-lab outline, correct? And you would have had that ready on the very same day that we did the experiment. That is not going to be the case, but you still are responsible when you submit your lab report for including an outline. Now, what's good about this is that we're going to make some changes here in the way the experiment is done. Let me show you the data sheet for this and show you what they're doing here. Okay, this is the data sheet here. First of all, this experiment was designed for you to use a solution of known molarity of NaOH. And as you can tell here, we're not doing that, we're doing KOH. Right? Now, notice the following. Over here, they say, what is the mass of test tube plus your sample? And then the test tube minus the sample. So the way they propose that you do the experiment is that you put some of your sample in a test tube and you weight it, and then you pour that sample into your reaction flask and then weight the test tube minus the sample. The assumption is that whatever difference there is in there is the mass of your sample. I don't know if you see the same problem that I see with this procedure. My problem with that is that I know myself, and I'm pretty sure that if I try to do that, I will pour my sample from the test tube into the flask and I'll probably miss it. That means that not all of the sample that I delivered ended up in the reaction flask. So I'm going to change the procedures for that reason, okay? So let me show you what the procedures we're going to do are. All right, so here we go. Let me zoom out again. Okay. So if you were doing this in the lab physically, you would be getting from our stockroom window a burette and a striker for your Bunsen burner. You'd bring your own test tube and you'd be given a sample of unknown. You're going to be given enough for 2 trials. From your equipment in your drawer or somewhere else in the lab, you'll have to get a beaker, a reaction flask, typically your 250 milliliter Erlenmeyer flask, which the video that I refer you to calls it a conical flask. You may need your Bunsen burner. And of course, you're going to be using your standardized KOH solution that you made and standardized in the previous experiment. Okay, we're going to start by tearing the flask. That means you put it on the balance and you hit the 0 button. And then you're going to add about half of your sample. See, now what you have is you're directly recording the mass of sample that's inside your flask. Okay, you're going to record that mass. Then, of course, since we're doing a titration, we're going to dissolve this in about 50 milliliters of water, obviously distilled water. And just like in the previous experiment, with the standard that you used, which was KHP, potassium hydrogen phthalate, you may need to heat over the flame in order to dissolve your unknown acid. So be careful with that. Do it carefully, do it gently. And once it dissolves, let it cool down back to room temperature before you add 2 or 3 drops of our indicator, which will be, again, phenolphthalein. Now you have your KOH in a burette. Of course, you condition the burette, you fill it with your KOH, you make sure there's no bubbles in there. And we're going to use that KOH to titrate our unknown acid to a faint pink endpoint. Remember that? Right. So on your data sheet, what you will have is, again, like I said before, you are not going to have this measurement here of the full and the empty test tube. You're going to record your mass of sample directly in here. Notice that we have KOH instead of NaOH, and of course, you're going to start with a certain volume in your burette, and then a final volume, which will allow you to determine what was the volume of KOH that was delivered. Now, you probably noticed something in here, and it is that they're putting in here HCl and a volume of HCl that was delivered. What is that all about? Well, let me explain to you what that is about. Remember that when you do a titration, you titrate to a faint pink endpoint. What happened last time, remember? Right. Some of us, when we try to do that, we overshot the endpoint. We went way overboard and overshot it. And what did we do back then? Well, what we did was we were told that we had to discard that titration and do another trial until we could get 2 good titrations that differed by less than 5% from each other. Well, so what happens here in this experiment? What if I overshoot the endpoint? Now, in previous trials, you would have been very sad indeed, somewhat discouraged. What if I told you that there is a way that you can continue the titration without having to discard your data? That's right. What we do is we take our reaction flask, which right now is showing a neon pink color, Vegas style. And we're going to do what is called a back titration. A back titration with a burette that has standardized HCl in it. Okay? It's usually going to take a little bit only. Now, why are we doing this? Remember, what does it mean that I overshot the endpoint? It means that I have excess KOH in that solution, and that's why the KOH and the indicator are having a party. But if I take my standardized HCl, where I know exactly how many moles I'm adding anytime I add a little bit of it back to my reaction mixture, I know that I can neutralize that excess KOH and remove the pink color. So usually it takes just a few drops, just a few drops. In other words, you're probably not going to need more than 1 milliliter of the standardized HCl. And what will happen is that now your reaction mix is going to be coming back to a colorless state because you neutralized the excess KOH, and you can calculate exactly how much of that there was. And now what you can do is you bring your reaction flask back to the burette of the KOH, and you can resume your titration with your KOH. And now, as we say in Miami, everybody happy. That's right. Okay, so back to our data sheet. That was the reason for these things in here. In other words, you're going to be given, you're going to be given a burette with some standardized HCl. And if you need to back titrate and overshot titration with your KOH, you can use that and calculate here how much HCl was required. And then you can continue and simply finish here putting in the initial and final. We will use our calculations here to adjust, in other words, to kind of figure out how much of the KOH that I added actually reacted with my acid, not with the HCl that I used for the back titration. Now, that being said, of course, when we finish our titration, we always have to deal with things. You are only going to need to do 2 trials here. Remember, since we have this back titration technique available, we don't need to discard any so-called, bad titration. There is no bad titration in this experiment. They're all good, all right? If you were in our campus physically, I would have asked you to save that KOH solution because we might use it in a future lab. Obviously, we're not going to do that. And also, you would have to discard your waste. You're going to basically pour your reaction mix down the drain because everything that we're using in this lab is non-toxic, safe. Now, remember, when I say pour something down the drain, it doesn't mean just pour it. It means you have to flush it with, some running water. All right. Now, a couple of things about the lab in its dry lab mode that we're doing. Realize that because we are not going to be able to, did I just get up? Sorry, I used the wrong sheet here. Because we are not going to be able to actually use the KOH that we made in our lab, what's going to happen is you're going to receive a data sheet that looks like this. It's going to have, of course, nothing here, nothing there, but it's going to have values for these different items here. It's going to have some kind of an unknown identifier. Okay, it'll be either a number, I don't know, 3, 5, 7, maybe a letter, A, B, C, something like that. And what you will do is you will use the data that you receive to write out your report. And in the next video, I'm going to walk us through a set of sample calculations. And I'm also going to discuss the questions in the post lab so that you guys know how to complete that. Okay. So this is the difference between doing the lab, physically in our campus labs versus doing it this way via Canvas. Okay. So before I go, let me remind you, please, that before we go to the next step, just remember to watch that other video that I linked in our Canvas page so you can review titrations. And that way you tackle this lab report as if you had actually done the titration yourself, okay? Try to imagine it, try to kind of like, embrace the idea of doing this lab for real, okay? In our next video, I'm gonna go through the calculations and the post lab. Thank you so much. We'll see you soon.